Welcome to the Introduction to Energy Management Training, Module 6. In this module, we will discuss energy management. Energy management can be broken down into energy and demand, energy baselines, energy management, and measurement and verification. Let's first have a look at energy and demand. In this slide is a typical load profile, depicting the load against the time of day. These will be different for whatever process is occurring within the plant. For this example, a conventional air conditioning unit is used, which shows us that the requirement for cooling during the midnight hours and night hours are a lot less than during noon, when temperatures are at its highest. This is likely driven by outdoor temperature as well as occupancy within a building. In this slide is an example of the incomers to Formosa Textiles for weaving and ring main during February. These are the averages during those periods. It shows that there is a spike, especially in weaving, from about 9 o'clock in the morning up to 1 o'clock, and then again from about 2 o'clock up to 6 o'clock at night. Ring main remains fairly constant during the day, with a slight dip between 7 and 10 in the mornings. The load factor is equal to the actual kilowatt hours used divided by the peak kilowatt times the time in hours. Let's look at the example below and compute the daily load factor. Remember that load factor is a measure of the utilization rate or the efficiency of electrical energy usage. So we can say that we know what the actual kilowatt hours used is, we know what the peak kilowatt is, and we know that the time is 24 hours. The load factor achieved is 58.3%. If the load factor is high, let's say above 50%, it shows that the power usage is relatively constant. If it's low, in other words below 50%, it means a high demand is set. For improving the load factor, electrical load operating at the peak time of the day should be shifted to non-peak times. Let's look at Formosa Textiles bill. We can see that for January to December 2018, the load factor for weaving was 75 and the load factor for ring main was 82%. Similarly, January to December for 2019, weaving load factor was 60% and ring load factor was 80%. This illustrates high potential for weaving to be optimized during peak times in order to avoid the kVA costs associated with a low load factor. Let's now look at the electrical demand versus the supply. Under power demand, we have the load factor. That is the amount of hours, total usage in time. The load profile, it's a shape of the usage relative to time. And we have management, mechanisms to change the above. It's shifting loads, shedding loads, and energy efficiency opportunities. The power supply depends more on quality. The influences the efficiency of and damage to equipment. Variation and imbalance, it changes over time within set parameters. And feedback effects, its own equipment on supply. Let's understand the concept of load shifting. So the red line on the graph illustrates before a load shift. That is to say, that is the actual profile. We can then say we shift loads to that period, period 2 and period 3 by reducing the maximum loads associated. Thus our overall maximum demand our kVA becomes less. In other words, we get billed less for maximum demand. With load shifting, there's no energy savings. Your kilowatt hours remain the same. You save only on the peak demand. So that is by reducing the peaks within this graph. It results in a demand cost saving. It should have zero impact on production. All we're doing is utilizing the dead periods, perhaps by having shifts overlap and having lunch times overlap and keeping the process running. And there's no environmental benefits to this initiative. Let's now look at load shedding and peak clipping. This is a bit different than load shifting. Shifting implies we move the load. Load shedding or peak clipping means we cut the peaks entirely, so we do not make up for them anywhere else along the profile. This will influence in a loss of production. It will have the advantage of an energy saving and a demand saving, and it's loss of income and energy of cost savings. However, this is still a viable solution should the opportunity arise. Next, we look at energy efficiency. We have our original profile, and we implement a few measures which brings the entire profile down to the second line on this graph, the dotted line. In this example, we will have energy savings, we will have demand savings, we will have cost savings. It should have no impact on production, and we will have efficiency savings. Let's look at an example of load shifting at Formosa Textiles. The red line on the graph illustrates the as-is. The green line on the graph illustrates the to-be. The only difference between these two lines is the difference that we use more energy in the morning hours, so perhaps we'll run slightly higher production, and during the day we run the same type of production and we avoid the peaks. This means our peak effectively jumps from about 3,600 kVA down to just about 3,200 kVA. That is a massive difference of 100,000 rands that can be saved in this one instance. It's necessary, however, to remember that kVA uses a maximum in 30-minutely data used during the entire month and applies that for the rest of the month. So it only takes one day that causes high costs on maximum demand. Therefore, this is the most critical part of energy management at Formosa Textiles, which needs constant focus and attention. On the electrical cost components, we have the admin charge, we have energy cost charge, and maximum demand. We also might have penalty charges which relate to power factor when we go over the amounts allocated. Next, we will go through energy baselines. The energy baseline is used for measuring the impact made on the energy consumption. It usually has a driver. In this case, or in Formosa Textiles case, the production is highly likely the driver to the energy consumption in the plant. The baseline period will have a measurement period where no interventions have taken place. The baseline period is a representative period of either 3 months all the way up to a year worth of data with the correct driver. This can be extrapolated to show what the future use would have been. And the difference can then be taken as the savings achieved for the specific initiative implemented. That is why it is extremely important for Formosa Textiles to have a steady and stable baseline set in place that can be audited and can be used to track future energy use and predict budgets accurately. Let's next have a look at energy management. Energy management is the use of engineering and economic principles to control energy costs in order to provide services in the buildings and industries. This produces the most savings in energy costs and improvements in energy efficiency. Other savings might involve changing the patterns of energy use and possibly shifting to other sources of energy. So let's have a look at how energy can be saved at Formosa Textiles. 30% can possibly save by changing behavior. Another 10 to 40% by operational efficiency. Another 5 to 10% for equipment efficiency. And up to 60% if new technology is brought into the plant. Let's look at the life cycle of energy management processes. First, the project identification phase will exist. Then, the phase that we are currently at, energy audits and assumptions that are being made. This following step is recommendations for implementation. We will likely need approval for funding if capital is involved. We would have to go through a detailed design stage, implementation stage, commissioning stage, and operation and maintenance. The current stage we are in is the energy auditing stage, and this is its subsequent phases as well. The identification of energy sources and costs, establish a profile of energy use and intensity, compile energy use inventory, establish energy use patterns, comparative analysis, and identify energy savings opportunities. Next, we will discuss measurement and verification. Measurement and verification has its own project stages and usually requires a dedicated team of measurement and verifications accredited experts. This course can also be offered to Formosa Textiles. These stages start with a scoping study, developing a measurement and verification plan. The plan would then need to be refined depending on whether or not Formosa Textiles gives their buy-in. We will then have the M&V baseline, which would also have to be refined depending on whether or not it is accepted by Formosa Textiles. We then have a post-implementation assessment, performance assessment, M&V performance tracking, monthly and annual savings report, and baseline adjustments. If the measurement and verification baseline is not correct, all the subsequent stages will be incorrect and cause disputes along the line. Therefore, it is extremely important to ensure that the measurement and verification baseline used is accurate and representative. Let's have a look at how energy efficient project and M&V project interactions interact with each other. The scoping report would likely come in from recommendations for implementation. You need to know where you are going to be implementing in order to set up a baseline for that section. Approval for funding. As an M&V plan usually costs money, the M&V baseline would have to be signed off before any implementation or any changes to the system occurs. And the post-implementation assessments all occur after the new initiatives have been implemented successfully. Let's now look at the benefits of measurement and verification. It's a substantiation of payments for performance, lower transaction costs in an energy performance contract, and international credibility for energy-saving reports. This means this can directly be tied back to your Higgs index and a credibility added to that. Next, we will discuss the different audit types. Let's look at the goals of an energy audit to start off with. Support a bigger energy management plan. It's not exact savings, but assumptions for business cases and paybacks. It's to determine if a possible solution is worth looking at or not. We do metering later to firm up assumptions and check the boundaries. A preliminary audit is to develop an understanding of the energy use and patterns. It's obtaining supportive data to do comparative analysis and planning. Audit plans determine the mandate and scope, types of the audit, appointment of a full team, and you also get a detailed audit. In this slide is an energy audit process flow diagram going from preliminary audit, audit plan, metrics, detailed audits, each with a unique set of requirements. Let's have a look at the 4 steps. So step 1 is preliminary audit. It's management, direction, and decision. It's to designate an energy management team and structure in place. It's supporting the collection of energy use and cost of data. It's ensuring support from personnel. Initial decisions on internal and external assistance. Then you conduct the preliminary energy audit. It's to obtain the historical consumption data, determine energy use and profiles, upper limit on savings, rates, and structures. It's to conduct a preliminary walkthrough audit to understand the layout, the energy, and in order to determine the energy management opportunities. We plot block flow diagrams of energy flow streams, actual power use versus the rates, compile energy use inventory and operating hours, to analyze the consumption and costs, and conduct a comparative analysis. We then decide on a future plan with internal or external assistance. We can now determine, in step 2 of the audit plan, we determine the audit mandate. We clarify goals, objectives, and key constraints. We develop framework for business case and align energy management opportunities with company's strategic intent. We define the audit scope. So we specify the physical extent of the audit's focus. We identify information types and sources, analytical approaches, energy systems, and their boundaries and subsystems. We then choose an audit type, determine the required accuracy, determine the implementation costs, and determine the base year. This is against which energy management opportunity implementation can be measured. Remember to timestamp savings. Determine and agree on changes to the base year. Step 4 is benchmarking audit. We benchmark against the industry. People don't know what is good or bad. We use to determine potential for significant improvement. Energy use index, megajoules per meter squared per year, and energy cost index, which is a rand per meter squared a year. The Higgs index serves as a benchmark for Formosa textiles, with its own criteria and subcategories in order to place Formosa textiles into the correct comparative state in order to benchmark against similar industries. Next, we discover step 4 in detailed audit types. We have a type 1, 2, 3 audit, investment grade audit, and a master audit. Type 1 audit is a detailed walkthrough audit. You need an experienced person. Target specific areas for inspection, metering and upgrade repairs, replace, establish and analyze energy use patterns, establish demand profiles, and establish complementary load inventory. Type 2 audit involves economic calculations. It can include metering to back up assumptions and expected identifications of opportunities and actual facts. Type 3 audit is computer modeling, detailed analysis, and annual consumption patterns. Investment grade audit is investment analysis including weighing risks used to obtain funding. Master audit is code compliance, develop maintenance schedules, equipment inventories, and so forth.